Okay, I think we're starting. I will get our screen share set up. And yeah. So yeah, last time we talked a lot about, well, the iterated bar construction, and that's what we're going to talk about this time. Last time we took it as a given that the iterated bar construction gave rise to models for Eilenberg-MacLane spaces. I'm going to outline a proof of that this time. Last time we focused more on homology, and that's what we'll revisit next time. But this time we'll go ahead and get some starts of details settled in there. So, right. So at the heart of this is the simplicial model for BG. So let me tell you, if you haven't studied classifying spaces before, um, again, this will just be a little invitation to learning more. So if I've got a contractible space on which a group acts freely, it's not so clear that such always exists, but suppose I find one, then I'm going to call the quotient, well, its homotopy type anyways is BG. So I could think of really, or I could just say EG mod G is a BG or something. There's these really are spaces where it's good to have multiple models, but we call all of them BG, even though, of course, they're not going to be the same spaces. And the significance of these spaces, well, they're kind of a canonical homotopy type that you associate to groups, and you end up studying them for many reasons. So, you know, if G acts freely on any space, so just if G is some sort of symmetries of the space, then there is up to homotopy unique way to map X to this EG equivariantly. So it will pass to the quotients. Yeah, and the proof basically is obstruction theory. You show that I can, especially for G discrete, this is fairly immediate. In any case, what this says is that if I've got some sort of space with group symmetries, naturally that category of space with group symmetries is sitting over this EG, or really the quotient spaces then sit over BG. So let's give you some examples before we get too far in developing the properties. So, well, if G is the group of integers, then actually it's a subgroup of a contractible group R, and therefore it acts freely. And so EG mod G in this case is just the circle. So sounds simple enough. Kind of similarly, if G is pi1 of an orientable surface, then we can take as EG the universal cover of the surface, which will either be the complex plane or the more in general, the Poincare disk. And our BG is again the surface itself. Okay. Um, More representative and very basic, of course, the groups that get you off the ground are cyclic groups of order n or prime order. And we're going to think of those inside the unit complex numbers. And the complex numbers then act on themselves. And the unit complex numbers act on the unit complex numbers. They also act on C2, C3, and the unit spheres within those, so namely S3, S5. And so, and those are free actions. So EG is going to, I claim, there's an action on S infinity. And a nice basic fact is that S infinity is contractible. You can use either the Hurewicz theorem, says it has no homotopy groups. And then the Whitehead theorem would say that because we can express it as a CW complex, it's contractible. Or you can use the fact that there's a cute little rotation. You can use trig functions to rotate the infinite sphere onto its equator. And then the equator, of course, is null homotopic through like an upper hemisphere. And so at that point, you've got a homotopy between the identity map and the constant map. Either way you see that, then you see that BG is some sort of lens space. So in particular, RP infinity when n equals 2. So that's kind of, so that's complicated, but not too far out there. In general, though, we'll see there aren't too many groups whose classifying spaces are super familiar like this. And part of the point of the bar construction, and then we'll use it as an iterated bar construction, is to make these more universally. But let's get to some properties. So these are homotopically unique. That's pretty easy. So again, I'll just assume sort of basic homotopy theory of fiber sequences, etc. So G to EG to BG is a fiber sequence. And suppose I've got some other EG prime, right? And I want to show these are equivalent. Well, I can just take EG cross this EG prime and quotient it, and I'll call that quotient BG double prime. And then you realize that, well, these projections, because EG and EG prime are contractible, this is an equivalence, and that's an equivalence, and these are equalities. And we can deduce from that that each of these are equivalences. So, yeah, so they're all homotopy equivalent to one another. They occur as D-loopings. In other words, as we'll see, the homotopy groups of BG are those of G just shifted by one. G could be a topological group here, in which case we want EG to, that action should also be continuous with respect to the topology on G. So how do we see that? Well, fairly similarly. So we're going to take our basic fiber sequence here, and we're also going to consider the path loop fibration. And what we can do is take the paths on EG, not based, but maybe those based at pre-images of the base point in BG. So you could also take the paths on BG and look at the cover, and then that's going to mapped to EG by, any number of ways, but you can take the endpoints of the path and you get a point in EG, and both are contractible. Or you could take the endpoint of the path and look at its image in BG. And you realize, though, that this is also a BG. So, and thus we get an equivalence here ultimately between G and loops BG. Okay, that was probably a bit brief, but let me say, rather than a property, this is an application. If suppose G acts on X, freely or not, you can form the quotient of X cross EG with G acting diagonally. This sits over BG, and it's pretty quick to see that there's a fiber X. And what you get from this, because this ends up being, if X is free, this ends up being homotopy equivalent to X. If X is not, this is an interesting homotopy type derived from that of X. And the cohomology of this middle term, is by definition Borel equivariant cohomology. And of course, the cohomology of this is the cohomology of BG, and that's the ground ring, because it, of course, maps to the cohomology of this Borel construction. And you see that the Borel equivariant cohomology, if you know the Serre spectral sequence, is some kind of twisted tensor, derived tensor product of the cohomology of BG and the cohomology of X. So these classifying spaces give you a tool to cohomologically measure any group action, and a very, theory. Okay, so the question is, well, do these BGs always exist for any G? And there are a few constructions that could work. I mean, one is if you get a construction for one kind of group, an EG, you restrict it to a subgroup, and you have an EH for any subgroup. So you could, for example, work hard at finding these for matrix groups. Turns out that's gets you into the geometry of Grassmannians. And then once you have it for matrix groups, it's any group which embeds in a matrix group, any linear group. But I'm going to share a different construction, which I'll call B delta G. And those who watched the first lecture should recognize this notation a bit. And it's just going to be the union. It's going to be similar to what we talked about last time. But we're going to take a K simplex instead of a product of an interval with itself K times, and K group elements. And then we're going to have an equivalence relation. And the way we'll think about it as, if I've got a T1 less than TK, comma or cross G1 through GK, I'm going to associate a picture to that, namely G1, G2, and these are happening at the T1 and T2 places. Okay, and with those pictures, then let me just say that the equivalence relation is defined by, well, if the ith one is, if the ith label is the identity element, then I can just ignore that point. Delete from both lists. So we had this kind of relationship last time with the iterated bar construction. Shouldn't be clear quite yet why that construction is so intimately related to this, but we'll get there in a second. Also, if some sort of ti equals ti plus 1, then what I can do is remove it from the list, multiply these, and then my gi plus 2 is now happening at what I'll call ti plus 1. So I'm removing the ti plus 1, previous ti plus 1 from the list, and multiplying those two group elements together. And that's what happens if they're crowded in the same point, if we want to think about the group elements living on points of the interval. And finally, if anybody's living either at the beginning or end, or both, well, we can ignore them. We can remove them from the list, kick them off the island. Okay. So, and what are some properties that it has that all other BGs don't necessarily? Well, one is it's functorial. In other words, if I have a group homomorphism, then it's pretty clear that I can apply the group homomorphism to each of these. Well, you have to check that the relations are compatible, but it's pretty immediate. There's a supports a conjugation action. So G acts on BG by conjugation, and this is homotopic to the identity. Let me give you the quick sketch of that. So I have, let me just do a G1 and a G2 versus conjugate both. So how am I going to relate these two? Well, I claim that there's a straight line homotopy where in between it's like this. If this is a you might have heard in the background my dog. If this is my dog, and the GG inverses are water. After going to the water, they can be shaken off, and the G1 and G2 stay where they are, but the G inverses and the G's are moving out to the left and the right. And eventually, they either go off the end or cancel. And you end up, there's a straight line homotopy, which conjugates the conjugation map, yielding a homotopy between this conjugation action and the identity. That ends up being really important in group cohomology. If you want to do calculations in Borel cohomology, the ground ring is this H upper star BG. And what this says, ultimately, you use it to show that the restriction homomorphisms between a group, from a group to its subgroup, lands in what's called the Weil group, the invariance of the cohomology of the subgroup under the normalizer. And so that's a really powerful tool for calculations. I'm sure it arises elsewhere. Right. The other thing is we can think of this as sort of geometric or explicit, although the geometry is limited. It's probably most useful for the argument I just gave you. Let me give you a couple examples. if G is a cyclic group of order 2, and we talked about this a bit in the first lecture, then remember that if I have anything labeled by the identity element, then I can just remove. Okay, and so what you end up with is a cell complex. So the other fact, which will become fairly immediate as we identify this as the realization of a simplicial set or simplicial space if G has topology, is that well, if G is discrete, then it's immediate that this comes as a CW complex. And in this case, there's one non-degenerate cell in every degree. And again, I remarked last time that the chains on this are the same as the cellular chains for RP infinity. In fact, perhaps with a little bit of futzing, you could actually make a homeomorphism. The attaching maps aren't exactly the attaching maps of RP infinity. They've got some sort of degenerate parts. So, for example, G E means that you've got this whole edge mapping to the base point in this attaching of the 2 cell to the 1 cell. And so that's not the same as having, only the G's labeling the boundary being identified to give you RP2. But obviously you could work a little bit and get a homeomorphism there. But in any case, it's certainly homotopy equivalent. I give this as an example just to illustrate. I mean, there, we can take G to be the integers, and you've got just points on an interval with these labels. And I just showed that these are homotopically unique. And the first example I gave said that for the G's, the integers I've got in S1. And what you can do is, is T or theta goes to, there's obviously a map where I just take the point 1 at time theta, if I'm thinking about the interval as parametrizing a circle from 0 to 1. Yeah, it's a good, you can trace through the arguments we gave, but I still have never sort of thought through if there's a better way to show that, so again, there's a map this way. Can we find a nice retraction back, which realizes this equivalence between one of the simple spaces we have and this interesting kind of infinite dimensional functorial, for example, model for it. Okay, so let's now set up the language machinery. I would call it language more than machinery at this point, to establish that this is this B delta G is a BG, so it's aptly named, and set up some things about it. So quick crash course. If C is a category, there's a simplicial set called the nerve, and then if you don't know simplicial sets, there's then a think of it as a simplicial complex, but again, depending on how we realize things, it might just be a CW complex called the realization of the nerve. And the 0 simplices of the nerve are the objects. The 1 simplices are the morphisms. The 2 simplices are the composable morphisms. So pairs of morphisms where one ends where the next begins. And so forth. And what you then do is you've got a sort of a picture of your category. So for example, partially ordered sets are categories. And so if I'm looking at, say, the subsets of the set 1, comma 2, the empty set sits in the singleton set 1, which sits in the singleton 1, 2. There's a unique morphism when I'm talking about posets. And you get this picture of this category. The picture, you get a space associated to the category when I realize the nerve, which is, again, it's capturing some things about the category. This is the singleton set 2. And that's a standard way to think about it. And again, the key thing is, if I've got objects A, B, and C, and then morphisms F and G, which then I can compose, then I fill in a 2 simplex. Okay, but I like to use what I call the interval model to sometimes reason about this. And what we do is just this point on any point in the 2 simplex is given by 2 points on the interval. And those are what I'm going to label F and G. So then it's natural to have the objects for the spaces between A, B, and C. Okay. And if I have this, say, just a little category with 3 objects and morphisms like this, and in addition to the identity morphisms, so the nerve, the realization of the nerve would be the 2 simplex. I'm just gonna that's homeomorphic to the set of all of these labelings on the of an interval and some points on an interval. And this then continues. It's harder to visualize, but of course, I can just take object 1. Take my first object and a morphism between it and my second object, and then a morphism to my third object, etc. So we just have, and if you want, if your morphisms, you're happy enough having them carry the load, you could just list the Fs. So it's just points on an interval with labels of F. But I like to remember that the Fs are transitions between objects, and that actually gives the labels of the space between. So the relevance of this is that that if we take a group, we can make a category, and I'm just going to call it script G. And that's just got one object, and I'll just even call it ob, and a morphism for every group element. And they compose in the way that the group law multiplies. And then the claim is that the nerve of this G, when I realize it, is my B delta G. All right, that's a pretty immediate translation between things. And part of the reason why this categorical language is nice to bring in is that we can also model EG. So namely, I'm going to define sort of a cover category of G, have one object for every group element, and then a unique morphism between pairs, any pair of group elements. So we'll take the complete graph and that's the, that is the category, is just the complete graph, and the composites just are determined by where you begin and end. And what I'll do though is I'll think of this morphism as a how do I want to do it? G1 inverse G2. So, and that's because there is a way I can act on G tilde, taking all of the objects to the single object, and then taking these morphisms to the GI inverse GJ morphisms, and you see that that's compatible with composition. And then the more remarkable thing is that, or then the remarkable thing is that the realization of this nerve is an EG. So it's contractible, and it has a free G action, okay? So these are various claims, and then finally its quotient is the B delta G. So let's talk about that a little bit. The fact that the quotient is the B delta G, this is because basically any, the composition in G tilde is going to determine and is basically determined by or sort of chains of composition in G tilde are basically one-to-one correspondence with chains of composable morphisms in our G plus a starting point. So really, this is sort of a covering space, covering category kind of thing. So that shows this quotient. The fact the group action is free, that's pretty immediate, because basically the group, because it really is on objects, and then that carries through to these chains of composable morphisms. And the fact that EG is that this is contractible, well, that's kind of fun. I claim there's a retraction onto a point, because if I take a point in this nerve construction, so it's, again, I've got some initial object I'm sort of starting on, because remember, this is I've got G's worth of objects. I'm ignoring any topology on G, which logically speaking for later isn't kosher, but all these things can be souped up to simplicial spaces rather than simplicial sets. So if I've got these chains of composable morphisms, and really it's just, I can only remember the objects if I want to, but then of course I've got these morphisms between. Okay, so if that's a chain of composable morphisms, I can start moving it to the base point by starting with being at the identity for a bit. And then I've got the morphism going from the identity to my G1. And, everything else looks the same from there. But of course, this time I spent at the identity element can increase until And then by convention, by the way, if there's no points, no morphisms, then I just have an object. And this is also why I like to label the spaces. I end up with, this is just the base point of EG. It's natural to, this construction of EG, this nerve of G tilde has a natural base point, namely that identity element object, its point. So yeah, so it just retracts right onto a point. So it's contractible. Oh, I didn't say that. It's contractible. Okay. So this gives a particular model. Now, one thing I like to do is, and I do like these models a lot. In fact, they're the centerpiece of talking about Eilenberg-MacLane spaces. That said, something I'll allude to in the last lecture is that sometimes there's other models, quote unquote, in nature that are helpful to consider. And part of the power of this subject is getting what you can out of different models for BG. In some cases, there's a nice geometric model and a nice manifold model, say. But of course, it's good to have the functorial models in the background. Well, one thing that's true about these models is that if A is abelian, then this B delta A is a topological abelian group. And that's, again, if we soup everything up to not just be simplicial set, but be a simplicial space, etc. So it's simple enough. This is by, we talked about this again, by union. So if I have A1 and A2, and then maybe a B1 where A1 was, and yeah, I don't need anything else. Well, maybe a B2 here. Then I'm going to, well, I've got A1 and B1. If I take their unions, their times are going to coincide. So that ends up being A1 plus B1, labeling this point. And then there'll be an A2, and then there'll be a B2. And you could wonder, well, could I do this without A being abelian? I could, for example, the question is, which order do I multiply them in? And it seems like because I'm choosing this to be the second element, I could multiply B1 on the right by A1. The problem would be continuity. So you could imagine if B1 starts out slightly to the left of where it was, if I had a B1 here, then the B1 occurs to the left of A1, and you then take a path to where it would meet up with the A1. And then the natural topology there would want that limit point to be B1 multiplied by the left to A1. Whereas by convention here, in the limit, we would be saying that B1 should multiply it to A1 on the right. So so you really need abelian here to play this game. And so that means then that we can take B delta of B delta A, okay? And, well, you start sketching this out. And lo and behold, if we take all those intervals and kind of think of where the second B delta is placing that line from the first B delta, that naturally fits in a square, and I can just remember where things end up. And that's what we defined last time as b squared delta A. And of course, we kept going. You can do it one at a time. All at once, we defined Bn delta A in terms of points in a cube with these labels. And then you have to track through all the identifications and see that, yes, they're compatible. As we go to any edges, things vanish as they should. Okay, so let's recall what we were doing with that last time. So if G is discrete, then as I said, because loops BG is G, that implies that BG is going to be a KG1. Okay, so and then, so that means then, but more generally, so BA is going to be a KA1. But the same fact, loops of BBA is BA, is going to imply that B squared A, I guess I can put my deltas, is going to be a KA2, and so on and so forth. So basically this loops B delooping property, and the fact that if A starts as discrete, will show that this iterated bar construction will have exactly one homotopy group, and that'll be A in whatever dimension that the B delta N is being defined. So this gives, again, sort of fairly concrete models. If you have, traditionally, if A is the integers, and most people would like to choose B as S1, and they also, it's known that KZ2, well, because S1 acts on S infinity, I talked about the cyclic group of order n acting on S infinity, but S1 acts on S infinity. You can then use an S infinity as an ES1, and then the quotient is CP infinity. And now this gives us an alternate way to make these things. So B delta Z is this interval with points labeled. KZ2 is a square with points labeled. And my point here is that there are models, but they aren't super familiar for what the next KZ3 is. But now, when I use the iterated bar construction, I can happily just think in similar terms. Okay, and that's what we do. Great. That's mainly what I wanted to fill in, saying that, yes, we've got these fairly concrete models. Again, it's not that we want to toss away all other models. In fact, power of the theory says that that it's useful to have multiple models. But let me give you a couple more ideas related. Extensions of these ideas. I'll be fairly quick. So namely, if X is any space, I can take points in X with, say, integer labels. I could do abelian group as well. So that's just going to be a union of x to the k. Maybe I want it based cross over sk z to the k with relations very similar to my b delta, my bn delta, right? And then there's a theorem that in that case, this space is homotopy equivalent, and this is the Dold-Thom theorem, is homotopy equivalent to a product of the k pi I x in degree I. So we talked about the Posnikov tower last time. This Zx has the same ingredients as the Posnikov tower of X, but there's quote unquote no extension. So it's kind of interesting way to think about, well, this is a useful and really interesting way to think about how homotopy types are built together from these pieces, with these abelian groups being the most sort of, there's no interaction between these the homotopy groups. Another little extension of these ideas is if A is an A infinity algebra, there's something which maybe I'll call BK for Stashev polytope, which generically looks the same, but in the E infinity context, if these points are in the same place, I need additional data to multiply, and that's provided by the Stashev polytopes. So the Kn is homeomorphic to a compactified configuration space of, well, basically I'll call it endpoints in the interval. There's really got to be some sort of boundary conditions there as well. So so you can take endpoints and then compactified configuration, and the point is that when things have quote unquote collided, if I have A1, A2, A3, then this compactification provides the data. If it's 3 points, I need another interval's worth of data to tell me how to multiply these. So this was basically Stashev's PhD thesis. Different language, you won't sort of see this perspective exactly there, but it's there. He makes a bar construction based on Stashev polytopes, is the short end. And the geometry of the bar construction is what we played with. Sort of taking some of these ideas, the previous two extensions together. Suppose M is framed, and say it's n-dimensional, and here's my M, and I'm gonna take an En algebra. So En algebra. It's okay if you don't know what that is. This is a sort of almost throwaway comment at the end, or perspective for those who know more. And I'm going to label points in M by the En algebra. But again, if points come together, I need some additional data, which if M is framed, I'm going to be looking at configurations of endpoints in M compactified, and then those as points come together in the tangent space, because M is framed, I get some sort of configuration, modulo translation, and scaling in the tangent space, which is canonically identified with Rn. So what you get is exactly the data I need to multiply these additional EJ, EK, EL, or whatever. And so this fits together in a sort of like a B delta construction. And what you get in the end is called the factorization homology of M with respect to E. It's factorization homology of M with coefficients in E. So examples are as we've given, the factorization homology in the circle for an associative algebra or an A-infinity algebra is just the bar construction. The factorization homology of an abelian group in a cube modulo boundary, so a sphere or a space, that's just this Dold-Tome idea. But now this is fully generalized to EN algebras, and it's a very promising theory that says that could tell us both about EN algebras if I fix, because again, bar constructions tell us about group elements. So I can think about this as potentially giving information about E, or the real promise perhaps is to be able to probe homeomorphism or diffeomorphism questions about M, probably more diffeomorphism, playing on that variable. So far we've focused on circles or spheres, but really, if you play with EN algebras, then you might be able to probe other kinds of manifolds. So next time I'm going to get back to homology. We're going to talk about Hopf rings, more about some other classifying spaces, and plenty of things like that. Okay, let's stop sharing and